Hello. Let's look at the oxidative reactions of the pentose phosphate pathway in this video. So these are the reactions. Okay, so it's fairly straightforward. We're going to go from glucose 6-phosphate. It's going to be oxidized. The electrons will make one NADPH. We'll get passed on to NADP plus to make one NADPH, and we're going to generate this product 6-phosphogluconolactone. And you can see how the oxidation state of the carbon changes here. Then we're going to hydrolyze gluconolactone, make gluconate. And then, by the way, we have already seen gluconate in the alternative upper part of glycolysis that we discussed in bacteria, just so that we connect this to the previous, some of the previous topics. Then the the 6-phosphogluconate will be decarboxylated, okay, to a 5-carbon unit here, and ribose 5-phosphate. And then in the process, we're going to generate also one more NADPH. Okay, so we're going to have oxidative decarboxylation at that point. So this summarizes, in a sense, the key products of the oxidative part of the pentose phosphate pathway, which is reducing power in the form of NADPH, and we get the 5-carbon units that we'll see then how they can be used. All right, so the first reaction, and we're writing again in our usual redox scheme, the oxidation state of the carbon. We have glucose 6-phosphate. Of course, glucose is an aldehyde, so that's the keto carbon, the carbonyl carbon here at the very end. And in this reaction, we're going to oxidize this carbon further to the carboxyl carbon state. Okay, so it's going to become an acid. And the electrons will reduce NADP plus to NADPH. So what is that? It's a classic redox reaction. And we have seen this again many times. Here on the structure, there is a hydride, so a proton with the 2 electrons that will move onto NADP. It's here, and we're going to get reduced NADPH. And the product here will be glucose 6-phosphate gluconolactone, which is shown on this diagram. So why bother? Well, we got reducing power. That's one of the major goals of the pentose phosphate pathway. So we got our NADPH, or one of them. We're going to get more, which of course is reducing power for biosynthesis. Then what happens is the following. Gluconolactone is hydrolyzed. Okay, we have a very simple, straightforward hydrolysis to get 6-phosphogluconate. What is that? Of course, it's a group transfer. In this case, it's the hydroxyl group of water. And it's just a general hydrolase. Now, why do we do this? Why do we go from the gluconolactone to the gluconate? It's necessary to set up the next reactions. Okay, so it's something that has to happen for the chemistry that follows. So what follows is this. So we have the 6-phosphogluconate. So it's all opened up now, the sugar. So remember, we had reduced aldehyde at the very end. When we started in the pathway, this carbon has been oxidized. Now we're going to oxidize another carbon, this one here, which is a hydroxycarbon shown in green, and that's going to be converted to a keto carbon, to a carbonyl carbon. Okay, and again, the electrons will be transferred to NADP plus to generate NADPH. The enzyme is 6-phosphogluconate dehydrogenase. Nothing special. We've seen 1,000 of those, before. However, in this case, what actually happens simultaneously here is the decarboxylation of 3-keto 6-phosphogluconate. So that's actually an intermediate in the whole reaction to give you ribulose 5-phosphate. So this is an unusual dehydrogenase because, again, it's coupled to decarboxylation, and there are only 4 of them. There are only 4 beta-hydroxy acid dehydrogenases, as they're called. Why beta here? If this is a carboxylic acid, that's the red. That's going to be the alpha carbon next to it, and that's going to be the beta carbon shown here in yellow. All right. So that's the dehydrogenase decarboxylase. how does it happen? All right, so it's actually a cool mechanism. So first we have the dehydrogenation happening. All right, so this hydroxycarbon will be converted to a ketocarbon, and again the whole hydride, the proton, and the 2 electrons of this bond will move on to NDP plus and become an NDPH. So there goes NDPH. Now with this carbonyl, okay, and you can guess why we needed that carbonyl here. With this carbonyl, the CO2 can leave. Why? Because if you decarboxylate and you break this carbon-carbon bond, okay, where would the electrons go? You have to stabilize the carbanion. So the carbonyl here helps with that stabilization because the electrons can bounce onto the oxygen. Okay, so you can lose the CO2, and that helps the reaction too. Okay, CO2 is a gas; it goes away. One of the products goes away, so you want to drive the reaction forward, and thermodynamically, and because it bounces back in the keto and enol configurations, now you can stabilize, as we said, the CO2 removal, and you end up with a 5-carbon sugar now in the keto. So it's a ketose, okay, ribulose 5-phosphate. And why do we do this? Because we now satisfy the production of the key products of the pentose phosphate pathway, which is reducing power and 5-carbon units, which could be used for biosynthesis if we need to, these pentoses, or if we don't need them for biosynthesis, we can reconfigure them as we will see in the sugar interconversion game, into something that can be used in glycolysis. So nothing goes to waste, right? And the overall reaction now is what we started with. We have a pentose and 2 NADPHs from glucose and oxidized NADP. So just to why do we deal with this in this way with a color scheme against, just to illustrate that we have redox reactions, and these show the oxidation state of the carbons. And the pentose, now we have this original carbon now that was at this position has been oxidized. And of course, the other yellow carbon here has been oxidized even more to carboxylic acid, which we lost as a CO2. And the overall scheme, again, is shown here. That carbon got oxidized to a carboxyl carbon, got lost in the form of CO2, and this carbon also got oxidized into a ketocarbon. So the name describing these reactions as an oxidative branch of the pentose phosphate pathway is very accurate. We have, here are your oxidations. We'll stop at this point, and then we'll see what happens. I mean, that's the mystery. What happens to this 5-carbon unit that we have? And we'll see that in another video in the non-oxidative reactions of the pentose phosphate pathway.